Welcome my friends! I'm so excited because in this video we get to talk about the hypergeometric distribution. So let's go ahead and get started. Recall the 4 requirements that were needed in order to use a binomial distribution. There must be a fixed number of trials. Each trial should have 2 possible outcomes, success and failure. Each trial should be independent, and the probability of success should be the same on each trial. Once we start modifying these conditions, we start to get different distributions. If we repeat the trials until we get our first success, then we have a geometric distribution. If there are more than 2 possible outcomes, we have what is called a multinomial distribution. If each trial is not independent, then we have the distribution that we are talking about, which is called the hypergeometric distribution. There are 3 conditions that need to be met in order to use the hypergeometric distribution. There must be a fixed number of trials. Each trial must have 2 possible outcomes, success and failure. But the difference here is that each trial should be dependent on the previous and should involve somehow sampling without replacement. Let's take a look at a few examples checking these conditions to see if we have a hypergeometric distribution. There are 15 balls in an urn. 10 are green and 5 are blue. You randomly select 3 balls and record their color. Now clearly this urn does not have enough balls in it, but this is just a visual representation of the idea that we have here with balls in an urn. So let's go ahead and check the conditions. Are there a fixed number of trials? Yes, we are going to randomly select 3 balls, so there will be 3 trials. Does each trial have 2 possible outcomes? Yes, there are 2 possible outcomes. We could either get a green or blue colored ball. Even if there were more than 2 colors, we could just say that one color would be success and the remaining colors would be failure, and we would still meet this condition. Is each trial dependent on the previous, involving sampling without replacement? Yes. Each ball is chosen without replacement. Once we choose one ball, we don't put it back in before choosing the next one. So therefore, since we have met all 3 of these conditions, this scenario can be modeled by the hypergeometric distribution. Let's look at another example. 20% of applicants for a job have the required experience. You continue to accept applicants until you find the first qualified applicant. Are there a fixed number of trials? No, the number of trials are not fixed. We're going to continue to accept applicants until we have the first qualified applicant, so we've already violated the first condition. Let's go ahead and check the others anyway. Does each trial have 2 possible outcomes? Yes, each applicant either does or does not have the required experience. Is each trial dependent on the previous, involving sampling without replacement? No, each applicant's experience is independent from the other applicants. As the first and third conditions have been violated, the hypergeometric distribution cannot be used to model this situation. You may recognize this as the geometric distribution when we're continuing trials until we find the first success. The hypergeometric distribution is typically thought to have 3 parameters: capital N, lowercase n, and r. Capital N is the population size, or the total number of objects that you are choosing from. For our example of the balls in the urn, this would be the total number of balls in the urn. Lowercase n is the sample size. This is the number of objects that you are choosing. In the example of the urn, this would be the number of balls that you are choosing. R is the number of successes in the population. This would be like the number of, let's say, blue balls that are in the urn. Now, unfortunately, there is no TI-84 function to calculate probabilities on the hypergeometric distribution, so we're going to have to use a formula. Unfortunately, the formula is a little bit complicated, and it involves the product of 2 different combinations on our numerator and 1 combination in our denominator. A simplified view of this formula is the first combination is choosing the number of successes, the second combination is choosing the number of failures, and the denominator is choosing all of the outcomes. I have to use the formula on the right rather than looking at all the details of the formula on the left, and we'll look at examples of how to apply this on the next slide. You can find the mean of the hypergeometric distribution, or the expected value, by taking lowercase n, multiplying by r, and dividing by uppercase N. There is a formula to calculate the standard deviation of a hypergeometric distribution, but it's a bit complicated and has been omitted. Let's look at an example. A group of 23 students are either business or non-business majors. There are 16 business majors and 7 non-business majors. If 5 students are chosen, what is the probability that 3 are business majors? Let's let our variable x represent the number of business majors chosen out of our sample of 5. x follows a hypergeometric distribution because we are sampling without replacement. Once we've chosen one student, we can't choose that student again. Our population size, represented by uppercase N, is equal to 23. There are 23 students which we are choosing from. Lowercase n, which is our sample size, is 5. We are choosing 5 students. R is the number of students who have the attribute or characteristic that we are looking for, which in this case are the business majors, and there are 16 business majors. Now to calculate the probability, you could use that complicated formula from the previous slide, but I'm going to opt to use the simplified version. Really what we have is 2 combinations which must be multiplied in our numerator, and then we're going to divide by a third combination. The first combination should relate to choosing our successes. In this case, a success would be a business major. The second combination is going to relate to choosing the failures, which would be the non-business majors. So you have to ask yourself, how many business majors are there? Well, there are 16 business majors, so the first number on this combination is going to be 16. How many business majors do we want to choose? Well, they tell us right here that we want to choose 3 business majors, so we're going to have 3 right here. How many non-business majors are there? Well, if there are 16 business majors and 23 students in total, well, then that would leave 7 non-business majors. How many non-business majors do we want to choose in our sample? Where our sample has 5 students and 3 of them are going to be business majors, so that means that the other 2 must be non-business majors. How many people do we have in total? Well, we have 23 students in total. And how many are we choosing? Well, we are choosing 5. So that's how you would go about setting up all of the combinations if you're using this simplified version of the formula. Once again, if you want to, just rely on all the letters, you can use that more complicated formula from the previous slide that tells you exactly what letters go where, but it's a little bit harder to deal with in my opinion. Now you can check your work to some degree in that this 16 and this 7 should add to 23, which they do, and this 3 right here and this 2 should add up to 5, which is the case as well. Now perhaps the most difficult part here is actually plugging this into the calculator. So let me show you how you could plug this into your TI calculator. See if we can get this small enough so we can see this a little better. Okay, so if you have a TI-84 calculator and it's a moderately updated one, you can actually create a fraction really nicely, and then that will make it a little bit easier to type these numbers in. So I'll show it both ways, but first I'll show it with the fraction. So if you want to get the the fraction set up kind of like we have here, press the alpha key, the y equal key, and then enter, and you will have the fraction. If that doesn't work, then either your calculator is not updated enough, or you may need to go into the mode and turn on math print mode. Okay, so then we can go and we can type in the combination. So we have 16 math, and we have to go to PRB. Option 3 multiplied by 7 math, arrow to PRB, combination 2, and then go to the bottom, and then we have 23 math, PRB, NCR 5. Press enter, and it should give you an answer. My calculator actually right now is set to give me fractions, so I can get out of that by going to math and going down to decimal, and this will give me the decimal form, which ends up being about 0.3494 or 3495 rounded to 4 decimals. So there's about a 34.95% chance that we choose 3 business majors. Now I also want to show you how to do this if we did not use the fraction option here. So then we could just do 16 combination 3 times 7 combination 2 divided by 23 math, left arrow, option 3, 5. And that should give us the same answer, and indeed it does. Okay, so a little bit more work than like the binomial PDF or geometric PDF, but still I don't think it's too bad if you kind of practice this a little bit. Let's also find the expected number of business majors from a sample of 5. So that's the same thing as asking for the mean, which is lowercase n times r divided by uppercase n. So just plug in the numbers if you've identified those up here. We have 5 times 16 over 23, which comes to 80 over 23, or about 3.48. So you'd expect that on average from a sample of 5, you get somewhere between 3 and 4 business majors. All right, so here's a problem for you to try. A drawer contains 7 black, 8 gray, and 10 white socks, all mixed up, and you're going to randomly grab 6 socks. What is the probability the number of white socks drawn is greater than 4? So X is going to represent the number of white socks drawn from the drawer out of 6, and we are asked for the probability that X is greater than 4, which is, since the maximum value that X could be is 6, since we're only grabbing 6 socks, this is really the same thing as asking for the probability that X is equal to 5 or X is equal to 6. So to find this, you're going to have to use that formula from before, plug in X equals 5, and then do it again for 6. So go ahead and give that a try, and I'll be back in just a moment to kind of help guide you if you're getting stuck or lost. But please do pause the video and give this a shot. Okay, probably the first thing you should have done is identify the values for uppercase N, lowercase n, and r. So uppercase N is the size of our population, or how many socks that we have. If you add up 7, 8, and 10, you should get 25. Lowercase n is the number of socks that you are drawing. We are drawing 6 socks, so lowercase n is 6. And r is the number of socks that have the characteristic you are looking for, the number of success socks, which in this case would be the white socks, right? And there are a total of 10 white socks. So I'm going to go ahead and fill out the values for the probability X is equal to 5. I'll let you do the probability X equals 6 and add the two together. So in this case, the first combination that we want here is picking the successes. And in this case, success is going to be represented by a white sock. And failure is going to be the second one, which is going to be any of the non-white socks. So first we have to identify, how many white socks are there? Well, there are 10 white socks. That was our value for R. And how many white socks do we want to choose? Well, we want to choose 5 white socks in this probability right here. So we're going to have a 5 there. How many non-white socks are there? Well, there are 15 non-white socks. Those are the black and the gray socks. And how many of those do we want to choose? Well, we're only choosing 6 socks in total. If 5 are white, that means the other 1 has to be a non-white sock. And then on the denominator, we have to have the total number of outcomes, which is 25. And then we are choosing 6 socks as our sample size. So the last number has to be 6. So go ahead and check your work as well. 10 plus 15 does equal 25. 5 plus 1 does equal to 6. So that checks out. Now I'll let you go ahead and plug those numbers in to get your answer. And then you can modify this so that this works for X equals 6 as well. Add those two numbers together and you will have your answer. All right, my friends, that finishes everything I wanted to talk about here related to the hypergeometric distribution. Hopefully you found it useful, and I will see you again in the next video.